Okay, great. Yeah, hi, my name is Michael Kigley, and I'm going to talk about CNNs in video analysis. In particular, I'm going to give an overview where I'm somewhat biased to fast methods. And the reason is that I work at this company where we, want to do things in production, so you have limited amount of time to do things, limited amount of processing power. And the reason we're interested in video analysis is because there's so much video being captured every day. Everybody in the Western world has a mobile phone. There's action cameras that you can really use in all scenarios. You can attach them to your surfboard, even to your dog. You can just take videos everywhere, basically. And this is also the reason why there's so much video these days. The latest number I found is from the end of 2015, but YouTube has 400 hours, or had 400 hours uploaded to it every minute, 400 hours of video. So there's really a lot of data being created and shared. But the problem is this data is often raw and not edited. So it doesn't have tags, it doesn't have titles. It's just, it's not edited to be nice to look at. And this makes it hard to look at it, to search for specific content, and so on and so forth. And to be able to do that, we need to teach a computer to understand visual data, or video data, in this case. But that's not easy, because video is really, first we have a lot of video, but then each video is typically 20 to 30 frames, so it's also a lot of data per second to process. And the second challenge is that it's often highly redundant. In this case, there's 2 frames that are 15 frames apart, and they're really very similar. So it doesn't really make sense in this case to look at all the frames, but in other cases, there's a lot of variation, a lot of frame-to-frame variation, so it makes it necessary to look at each frame. So that's basically where we are. So in this talk now, I'm going to talk about 3 applications in video analysis. One is video analysis for action recognition, so classifying what action is shown in a video or in a short snippet of video. The second is shot boundary detection, where the goal is to figure out where a shot change happens. And then lastly, I'll give a short demo where we put these 2 things together to automatically detect what's the most interesting part of a video and create a GIF from it. But first, I'm going to give a background on what CNNs really are. And here's a small illustration. Basically, they're end-to-end trainable systems that can take an image or a video and, through some transformations that can be learned, give a prediction on what's happening in this image or video. So this is a bit mathy. So basically, it's quite simple. A neuron is really simple. There's basically some input X and some weight vector W. And the activation of a neuron is just a dot product between the 2, offset by some bias. And then typically this is put into a nonlinearity, which just thresholds everything smaller than 0 at 0. So a neuron is either has a 0 activation or a positive activation. This is illustrated here graphically. For a standard neuron in a neural network, you have it that each neuron sees the complete input from the previous layer. On the first layer, that's the pixels, and then later on, that's the activation from previous neurons. Now in the CNN, it's actually quite similar, but each neuron doesn't see the complete input. It only sees a small part. And then the convolutional filters, these weights, are basically moved over the input to compute an activation. So this is visualized here. This is basically showing one neuron that's moved over the input. And at each input, it gives an activation. So the output would not be a single activation for this neuron, but it would be an activation map. And the standard neuron would just take the complete input. So it just have an activation map that has one output, right?
Sorry, at the previous slide, is the data flowing from top to bottom?
Oh, sorry, no, it's from the bottom to top. So, yeah. So basically, these are, each of these gray squares is basically the weight that is put to this input. And then, it's just, basically a weighted sum, right? That leads to the output. Okay, so why do we care about CNNs? The first thing is that once we go to high-dimensional input, like images, fully connected neural networks that I explained in the first or 2 slides ago would just have too many parameters to learn the parameters. So it'd be, like in this example, so here a CNN would have 4 by 4, an input of 4 by 4 pixels, so 16 parameters, one neuron in this case. If it looked at the full input, it would be roughly like 10 by 10, so 100 parameters already. But once you go to natural images, of course, you have much higher resolutions. So it becomes infeasible to actually train a fully connected neural network. Second reason is that they're faster at inference and also faster to learn because, well, there's weight sharing. And what they actually do, what Anna already mentioned, is they assume translational invariance. So that means that, the weights are the same for different positions. So basically the assumption is that it doesn't matter where some input in the image occurs. Okay, so that are the basic. Now I'm going to talk about spatio-temporal features with 3D convolutions. And it's really the same thing. 3D convolutions are just exactly the same thing, except now the input is not 2D, but 3D. And the filter that is computed, the convolution, is also in 3D, which means the output is, again, a 3D map rather than a 2D map. And in particular here, I'm going to focus on C3D, which is a typical or widely used neural network that uses these 3D convolutions. And the reference is here on the bottom. So basically it takes a standard architecture like AlexNet from image analysis and replaces the 2D convolutions with 3D convolutions. This allows to analyze blocks of frames. And in this case, in C3D, it uses 16 frames that it analyzes at once. So it can also learn about motion and change over time. And the network that I described is trained on Sports 1 million, which is a data set of different sports out of 1,000 classes. And the task is then to, given a snippet of video, to classify what sport is shown in the snippet. And examples are boomerang, throwing a boomerang, bowling, and so on and so forth. Now, if this model is tested on another action recognition data set that's commonly used, we can see that it improves hand-defined methods. And what's more interesting for me is that it does so at 100 times the speed. So it runs at more than 300 frames per second. So that means it runs 10 times real time. Of course, you get better accuracy if you combine this C3D, this 3D convolutional neural network, with hand-defined features. But then, of course, you're back to the speed, the low speed of the hand-defined method. Last year in NIPS, there was another paper that had quite a bit better performance, but it uses optical flow as an input to the network. And that it runs at 34 frames per second. So just computing the input is 10 times slower, roughly, than running the full C3D model. What's also interesting is that this model is very general. So it was trained for action recognition, but it also works well for scene recognition, for object recognition, and for action similarity. And here's the visualization of what C3D learns. So basically, this is a projection of the features it learns to 2D. And each color here represents an action. And you can see that it better separates the different actions than a network that's trained for ImageNet. So that doesn't have this motion information. What's also interesting, other than the speed that I mentioned, is that it's easy to implement. It's really simple blocks. It's just 3D convolutions, some pooling, and that's basically it. As such, it's widely used in industry, and there's the original Kafka implementation available. I also did a Lasagne implementation because I prefer Python. And there's a Keras implementation as well. But you should be careful because some of them are actually wrong. So don't trust anyone except maybe me if you want. Good. Okay. So you can use you can use 3D convolutions also for other tasks like shot detection. And I should say what shot detection is first. So the goal of shot detection is to split a video into shots. And a shot is a consecutive set or a set of frames that shows continuous progression of events. So it would be everything that naturally happens, for example, due to a moving camera, due to objects that move in a scene. But it wouldn't be changes like the one here shown on the bottom, where an editor combined different shots together with some transitions. So you want to detect when something like this happens. And this is important because it is useful for action recognition, it's used for video indexing, and also actually, as I'll show you later, it's used in highlight detection. And as such, it's really an important pre-processing step. That is also why it has been researched for more than 25 years. And you would think that, after 25 years for a simple task like this, right, it should be solved. But that's not the case, and here's why. It's actually pretty hard. So now comes the interactive part. You can guess which of these pairs basically shows a shot change for A, B, and C, and which one does not. So does anybody want to guess? A is what? That is wrong. Because, it's very hard. So A and B, I would say, are quite similar because it's just like a cut. It's non-continuous, right? But typically, the A is considered not a shot change because the abrupt change happens in the background and the foreground is continuous. And in B, it's the other way around. It's that the background stays the same, but the foreground is non-continuous. So this is typically considered a shot change. And in C, we again have no shot change. It's just that there's a camera flash, which is natural, but the scene progresses afterwards. So this shouldn't be considered a shot change, which makes it hard, right? Well, what can you do? The simplest thing is to just use C3D, this 3D convolutional architecture I presented for action recognition, and apply it for shot detection. And there's actually a paper, a very recent paper, that does this. I should also say this is the first paper, together with mine, that I'll present afterwards, that used CNNs for shot detection. Now the problem with this C3D architecture, when you use it for shot boundary detection, is that it takes 16 frames at a time. So what you get is you get a prediction on what happens in these 16 frames, but for shot detection, you want to know exactly where a shot change happens, right? So it's not frame accurate. Or you can make it frame accurate by just putting 16 frames in, moving it by one, again, 16 frames in. But this makes it very redundant and would lead to a network that looks at every frame 16 times. A better approach is to use a fully convolutional architecture, fully convolutional in time. This allows to be frame accurate in the labeling, and it allows to reuse activations of convolutional neurons. And this is what I did in this recent work, also from last month. And basically the idea is, as I said, to be fully convolutional in time. So now we don't move the convolutional filter in space, as I've shown in this illustration before, but we move it over time. And this allows to reuse activations of neurons. For example, for the last prediction on top, we would only really need to compute this last set of activation maps. This means we can make frame-accurate predictions by just looking at each frame once. And because of that, our method is very, very fast. It runs at 120 times real time on a GPU, so you can analyze a full-length movie in less than a minute. And actually, it's so fast, the bottleneck is now resizing the frames to put them into the neural network and not the processing itself. And also, I should say, the method is more accurate than previous works, while being significantly faster. Now, if you didn't have this fully convolutional architecture and did basically the naive method that I show here on the left, you just take 10 frames, run them through the network, shift by one, and iterate, then, of course, it would be much slower. And there's the number there, roughly 14 times real-time speed. Okay, an important part of our method is actually training data, because if you want to train a deep net, especially if you want to train it from scratch, is you need training data. But for shot detection, it's really simple. And the key insight is that, I mentioned this earlier already, is that all shot transitions are manually added. Basically, at some point, there's raw video coming from somewhere, and then an editor takes it, chops it into pieces, and recombines the parts he wants with some transitions. And we can actually do the same automatically, and then we have labeled data. We know where a shot change occurs, and we can use that for training. And actually, the model I showed that obtains state-of-the-art performance is only trained on this kind of data. So there's no manually labeled data used. And to train it, I just generated the most frequent transitions, like hard cuts, dissolves, where basically one shot dissolves into the next one, fades, wipes, and so on. Okay, well, finally, now we have a good system for recognition, and we have a good shot detection system. And what we did is we put these together to automatically detect highlights in videos. And with highlights here, I mean basically shots that would make good GIFs, that would look good as a GIF. And the approach we use is we use a rank formulation. So we learn to score good shots higher than bad ones. And you see some example here. It's kind of small, but basically we have a bunch of training pairs, and the goal is to give a higher score to the ones on the left than to the ones on the right. And to do that, we train a neural network based on top of C3D, actually. So we use C3D features to rank these pairs. So we minimize the rank loss that basically penalizes having wrong order of these pairs. A crucial thing, again, is training data, which is really a recurring topic, I guess, in deep learning. And it's something that we have at the company because we're a website to create GIFs from videos, typically from YouTube videos. So we have more than 8 million GIFs created from video. And what GIFs really are is they're the most interesting part, or they're made from a human that tells us, hey, this is what I think is the most interesting part of the video. And here's an example of a user who basically manually edited out a scene where a guy scores a goal in soccer. So we have a lot of this data, and we use a bit more than 200,000 videos to then train our neural network to figure out what is an interesting GIF. Or what is an interesting shot, what would make a good GIF. And here's some results. I had a paper, when was that? Last summer. But now we had some improvements in the company. But this is not super important. I just suggest you go try it out. If you're interested, there's a link. You can just go to gifs.com and it will guide you there. And I have an example here where I looked at a travel video from Zurich, where there's some woman flying to Zurich and, explaining what she does and visiting random places, or maybe more famous places than random places in Zurich. And if we put this into our system, I should say I pre-computed this before, so it's just cached. It's not that fast usually, but it's roughly 30 times real time. Here are the results. I think it does a pretty good job. So our network has learned that people talking into the camera are not that interesting. Unlucky for me, because there's a camera at the back. Anyway, so it picks up things where there's actually, actions, where there's objects centered in the video, like here on top. So I think it does a reasonably good job. I should also say here we diversify the results so that we don't get very redundant segments proposed. Okay. So that's already it from my side. To conclude, I have shown you that 3D convolutions are generally applicable. We have seen 3 applications, one being action recognition, the second one, shot boundary detection, and finally, highlight detection, which is also based on C3D. They're kind of brute force because they don't bother about whether something is redundant or not. They just process everything, but they're very fast. So in my opinion, at this point, they're the best engineering solution. They're the best solution if you need to do something fast. And my background is that I did a PhD in video summarization, which is exactly the scenario where you have a lot of data. So it should be processed fast, right? But they're kind of brute force. So I think an interesting future research, an interesting topic that also ties back to Anna's talk is adaptive computation, where a network would automatically figure out where it needs more processing power, spend more time on processing, like the eccentricity model. And there's a model that does that, which is called soft attention, but it actually still processes everything and just reweights it So it's not any faster, it's just a bit more accurate. But what we really want is we need something that is much faster, that guides its attention, its computation time to important areas. So that's it from my side. Here are all the links you need, our website, our Twitter, my Twitter. The slides are also online. I hope I set them to public, but if not, I'll do it after the talk. There's also a lecture on CNNs that I like, if you want to check it out and don't know this stuff already. And of course, code for C3D. Any questions? Yeah? And you know MMR, maximally marginal relevance? Yeah. So it's basically, it selects elements that score high but are different from previously selected elements. That's like the rough idea. Any other questions? Yeah?
When you showed the two projections, you remarked that the C3D has a better separation capability. Since I'm not familiar with the projection technique, I mean, how do you know that your separation is better and not just that you pick the wrong projection to 2D from the imaging dimension?
Right. Yeah, that's a good question. So this is not my method. This is from their paper. Yeah, it's kind of hard to say. There's certainly, a lot happening when you project high-dimensional data to 2D that is not always obvious. But I guess TSNE is considered the state-of-the-art for projecting stuff to 2D. It's also based on neural networks. And I wouldn't take this, as the final word on it. It's more just to visually illustrate that it does a good job on related tasks. So the key message here is it works for things that it's not directly trained on. Yeah?
Did it happen that the network had the moments where you saw some video which didn't seem interesting and suddenly you had the interesting moments? So did it have moments when it detected the interesting moment a little bit ahead of what a human would do?
After, you mean, or?
No, ahead.
Ahead.
Start a certain sequence where initially there was nothing happening and then suddenly an interesting moment popped in.
Right. So you mean it would realize earlier that something interesting is going to happen? I didn't go this deep in the analysis, to be honest. Yeah, I guess, so we usually assume that we have the full video once we start processing. So you're more talking about an online algorithm where basically, the network tries to figure out as it goes what's going to happen, right? Or if something, yeah. I can't give you an answer. I think it's an interesting question that would be useful, for example, I guess in surveillance, traffic monitoring, where a human could be alerted to look at a camera, right? So that's, I guess, a useful application, but we didn't look into that. Yeah?
Has the tracking been associated with any emotion or sentiment analysis?
For the automatic GIF creation. No, it's kind of... So yeah, I mentioned this as an example. So what we find is that there's... typically, it doesn't tend to select faces. I think it does detect when there's like laughter or some unusual, or some more like, let's say, more action going on rather than just a person talking. I wouldn't say it goes as far as actually detecting the emotion, but it detects that it's not just somebody talking, let's say. There was another question somewhere. Yeah?
Is there any comparison between using 2D convolutions frame by frame and then using RNNs versus C3D?
Yeah, there is. Sure. So you can use RNNs to do temporal aggregation, which tends to work well, but it comes at a computational cost. Yeah. So it's more also for, I guess, for action recognition, what I mentioned at the beginning. That's helpful because you want to classify potentially a longer input. For highlight detection, you really want a short snippet, to pick a short snippet, so you don't have this problem that you need to aggregate information over a long period of time. But yeah, this is a good method that people use. So C3D is like, I think, the industry standard because it's fast. But you know, once you want to spend, I don't know, 10 times, or like if you want to process at 1/10 of real time, then you can do much more complicated things, of course. I'm not saying that RNN is that bad, but you know, it's already another layer of computation.
You said that resizing takes a lot of computation compared to the actual computation. I just wonder, to what effective resolution do you sample down?
Oh yeah, so
3D, I wonder, what's your resolution in like how many frames do you consider in one?
where was this? Yeah. That's for the shot detection. For the shot detection, I use 10 frames to have some context on what happens right before and after, right? And I processed at 64 times 64, so very low resolution, based on the assumption that you don't need to have the fine details to know if there's an abrupt change or if there's a dissolve. This is really something that is less subtle, I guess. There's a question at the back, I think.
It was a similar question.
Okay. Okay.
The last question, could you give more details on how you generated the training data? Like, for instance, if a user uploads a video, it's already like a shot. Were you combining two different uploads and then generating like a transition between them?
So basically, I collected raw video that doesn't have any shots, and then split them into small chunks and recombine these chunks. So basically, you need raw video of which you know there's no transitions already, because otherwise these will be false negatives, right? They would be labeled as non-transitions when in fact they are. Yeah. Does that answer your question? Okay.
Where did you get the video without any shot transitions?
Manual labor. Watching a lot of YouTube videos. Yeah?
In the beginning, you showed these quite special cases of shot transitions.
Right.
So how well does your model then perform on these special cases?
Yeah, so I didn't say for C, we're interested in sports analysis, so it happens a lot that there's camera flashes. What I did is I actually artificially generated frames that have flashes explicitly to train the network to be invariant to that. So it's not a false positive. So here on C it does the correct thing. It does the same on B, but for A, this is a false positive where it thinks there's a shot transition, which is also, I guess, quite subtle. And you know, for these partial transitions, we didn't train for them. And what's more, I think it's really a complex task in this case, because the network would need to get an understanding on what's foreground and what's background. Yeah?
Are you also using sound, or have you thought about using sound?
For the highlight detection, yeah, we do use. I think there's audio. So we do use audio. We don't use speech recognition, so we have a network that we actually did at the lab here at ETH that also does detect environmental sounds, so like clapping, cheering, and so on and so forth. And we use that. The contribution is small, I think. I guess also, you know, when you want to detect highlights, and especially if you create GIFs, obviously the sound doesn't play a major role, because otherwise you wouldn't choose the GIF format, right? An more interesting application, I guess, is actually speech recognition to automatically put subtitles for example. Yeah?
So you said in the beginning that your convolutions are not overlapping because that would be very redundant. But for example, in highlight detection, it may happen that your highlight may be missed between two separate convolutions. Say 20 frames here, 20 frames here. But the highlight may be the last 5 frames of this or the first 5 frames of this. So if the network does not remember a state or some sort of.
Right. So yeah, I guess that's a valid point. So what it does is it does per shot or basically it takes C3D aggregated over the shot and predicts a score on this shot. So I guess in that sense, yeah, it doesn't really, like ideally what you would do is you would basically feed the whole thing into the network and it would choose, you know, the start and end, the boundaries of the GIF as well, right? But we have basically shot detection as a pre-processing step and we just score shots. So I agree that's something that that's maybe a more special case, but that we can't tackle. Okay, well, I think, and then let's wrap this up. Thanks for coming. Do you want to say a few words, maybe?
Thank you very much.
Okay.